Now, when we say we have a desired current, of course, when calculating, I have it in my mind that it should be 200 microamperes. In terms of circuits, what it means is that there is a current source of the desired value available. Okay, that means that I have a 200 microamperes. Let me call it in general as I naught. A source of value I naught is available. Okay. How to make this current source we see later, because in an electronic circuit everything has to be made using transistors, and there are ways of making a current source also using a transistor. Okay. So this current source is available, and what is it that we want to do? We have a transistor, and the drain current of this must become equal to I naught. And of course, directly connecting I naught to this doesn't work. We saw that because the transistor is a unilateral device. So what we need to do is to adjust this gate source voltage, and as mentioned here, we'll control the gate voltage and keep the source voltage fixed. Okay, I can fix this to any voltage, but I'll tie it to ground. It doesn't matter what voltage I connect it to. For now, let's assume it is at ground. So what I have to do is, this is the gate voltage Vg, and I have to control that and somehow come up with a circuit arrangement. This is not something I am doing manually, right? I am not looking at an ammeter and adjusting it. I should configure the circuit so that finally, when everything settles down, this value of ID should become equal to I naught. Okay. So as we described the process of negative feedback, there are two things to be done. Compare ID with I naught and adjust the gate voltage Vg. Okay. So depending on whether ID is more than I naught or ID is less than I naught. Now how do we compare two currents? Okay, when we say compare, essentially I want to know whether ID is more than I naught or less than I naught. And one of the common ways of doing this is to look at I naught minus ID, or you can also look at ID minus I naught. So the sign of I naught minus ID, if I naught minus ID is positive, I know that my drain current ID is too small, and if I naught minus ID is negative, I know that ID is too large. Okay, so based on that I can do something. So essentially I need to be able to take the difference between two currents, or algebraically sum of two currents. Okay, I hope this part is clear. We have to compare two currents. That means that I have to compute the difference between these two currents. In other words, some sort of algebraic sum of the two currents. Okay, and how do we sum two currents? We know that by Kirchhoff's current law, if you connect two currents into a node, then the current that is flowing out of that node will be the sum of these two. Okay, that is, if I have I1 and I2 flowing that way, what will be flowing out is going to be I1 plus I2. On the other hand, if I had I2 in the opposite direction, I would have got I1 minus I2. Okay. So simply by connecting currents to a node, what tends to flow out of the node, we'll have to see what happens to that. What tends to flow out of the node will be the sum of the currents. Okay, which is exactly what we want. So what do we need to do here? Here we need to find I naught minus ID. So if I connect these two together, okay, let me show it like that. What tends to flow out of this node, I have not connected anything there yet. Okay, so what tends to flow out of there is I naught minus ID. I hope this part is clear. This is just basic Kirchhoff's current law. Okay, so if I naught is flowing in this wire and if ID is flowing there, what goes out has to be equal to I naught minus ID. Okay. Now where does it really go? Right? When you do connect it up like this and you do have two currents which are different, what happens? In case of ideal current sources, we say that such a connection is not permitted. Okay. So such a connection is not permitted because it violates Kirchhoff's current law. Okay, but of course nothing prevents me from taking two things like the transistor and the current source and connecting them together. And what really happens in that case? What happens is the following. At every node, there will be some parasitic capacitance. Okay, you know that anytime you have two conductors separated by some dielectric, there will be some capacitance between them. So that means that if you have a circuit with a number of wires, there will be capacitors from every wire to every other wire. Okay, so you can think of this in order to figure out what really happens when I naught is different from ID. You can think of this as flowing into a capacitor. Okay, the capacitor can be connected anywhere, it doesn't matter, but we'll assume that it's a capacitor connected to ground. Okay, the result of what we are going to discuss doesn't change regardless of the connection of the capacitor. Okay, so it flows into a capacitor. This capacitor can be arbitrarily small, it doesn't matter. That only says how fast the voltage here changes. Okay, just to be able to satisfy Kirchhoff's current law, this current has to flow somewhere and it will flow into the parasitic capacitance associated with that node. Okay, so again, I hope this part is very clear. Otherwise, again, please go back and think about it. If you have two currents coming into a node and those two currents are unequal, the difference will flow into a parasitic capacitance. So what happens because of that? It's very clear. If ID is smaller than I naught, this means that I naught minus ID is more than 0. So current is being pumped into this capacitor. The voltage across this capacitor goes up. Okay. And what does it mean? This is ground, this is the drain voltage VD, the drain voltage VD increases. Again, this is basic behavior of the capacitor. If you are measuring the voltage of the capacitor like this, and if you pump a current, positive current in that direction, okay, what happens is this VC will go on increasing. Okay, that's because VC is 1 over C integral I dt. We don't have to worry about exactly the shape of the current or the voltage. All we need to know is that if the current is positive, the voltage will go on increasing. Okay. Now conversely, if ID is greater than I naught, that means that more current is flowing down than what is being pumped in. So this current will be negative. Current will be actually drawn from the top plate of the capacitor. VD falls, the drain voltage falls. Okay, that is, if you have a capacitor, you are measuring the capacitor voltage like this, and if you have a current in this direction, this VC goes on decreasing because you are taking charge out of the upper plate. Okay, so this is what we need to know. Okay, we need to know that VD increases or decreases based on whether I naught is more than ID or I naught is less than ID. Okay. Now, what is it that we need to do? Okay, earlier I was looking at the ammeter and doing this, but now I need the circuit to automatically do this. What should happen if I naught is more than ID? If ID is smaller than I naught, what should I do? I know that ID is too small. I have to increase the value of ID. So that means I have to increase the value of VG. Okay, because ID is an increasing function of VG, right? We know that ID versus VG, it's the square law. It looks like that. So if I have to increase ID, I have to go from there to there. I have to increase the value of VG. So if ID is smaller than I naught, we must increase VG, and if ID is greater than I naught, the opposite. That means that ID is too large, we have to make it smaller. So the way to make it smaller is by reducing the value of VG. Okay. So this is the action we need. This is the feedback action we need. Now, how do we configure the circuit so that this automatically happens? If you look at it, look at what the drain voltage is doing. If ID is smaller than I naught, VD is actually increasing. That's because this difference current flows into the parasitic capacitor and tends to increase that. Okay, and it's exactly the same as what we wanted for VG. Similarly, if ID is greater than I naught, VD goes on decreasing, and if ID is greater than I naught, we actually want to reduce VG. In other words, what we want to happen for VG is already happening at the drain. What we must do to the gate voltage is actually happening to the drain voltage simply because of this connection. Okay. So now the solution is pretty obvious. All we have to do, or one of the ways to do it, is to somehow transfer this VD to VG. Okay. And the easiest way to do that is to connect the gate to the drain. Again, what we desire for VG, the kind of variation we want for VG, is happening at the drain, right? So the easiest thing to do is to make VG equals VD. That gives us the first type of circuit. This will be connected somewhere. I'll assume that it is connected to some supply voltage VDD. This is the current I naught, and this is the actual drain current ID. I naught minus ID will flow into this capacitor CP, which is the parasitic capacitor. Don't worry about its size. It's just to imagine the kind of voltage variations you get at the drain. Okay. And let's say we connect the drain to the gate. Okay. Because of this connection, we make VG equals VD. What happens now? If ID is smaller than I naught, some current will be flowing into this capacitor and this voltage will go on increasing. On the other hand, if ID is more than I naught, some current will be drawn from the upper plate and this voltage will go on decreasing. Okay. And if ID is greater than I naught, VD decreases continuously. Okay. Now, when does VD stay constant? VD will stay constant only if ID exactly equals I naught. Now, let's say what happens because of this connection. Okay. Let's say ID initially was smaller than I naught. When you start off, maybe it starts with 0 current. Okay. Then the drain voltage goes on increasing. Now, what happens in that case? The gate voltage also goes on increasing. So this increases the value of ID. Okay. So ID is smaller than I naught. So this ID will go on increasing because of this feedback. Okay. So it's exactly what you want. Or if ID is too much, if ID is higher than I naught, then the VD will go on decreasing, which will in turn reduce the gate voltage, which will in turn reduce the drain current. Okay. So in other words, if in this particular case, what happens is VG increases, which implies that ID also increases. And in this particular case, VG falls down, which implies that ID also falls down. Now, in either case, what will happen is both of them will end up at this state. Okay. So in this case, because of this feedback, ID will go on increasing. We don't have to worry about whether it's slow or fast. It will keep on doing that until I naught becomes exactly equal to ID. Okay. So in that case, it will stop. And exactly the same thing happens in this case as well. In this case, ID will go on decreasing until it becomes exactly equal to I naught. Now, if it is not equal to I naught, we know that the circuit won't reach steady state because this voltage will go on increasing or decreasing. Finally, when this voltage becomes constant, we are guaranteed that ID is exactly equal to I naught. That is simply by Kirchhoff's current law. Okay. So this is the most basic way of biasing a transistor, and this is known as drain feedback. What it really means is that the drain source voltage is fed back to the gate source. Okay, the gate source voltage equals the drain source voltage in this case. So the drain voltage is somehow fed back to the gate, and finally steady state is reached where the drain current of the transistor equals the desired current I naught. What I want to emphasize very strongly is that if you look at this circuit, don't think of it as I naught being somehow applied to the transistor. Okay, this is a feedback circuit. The difference between I naught and ID triggers some feedback action that controls the gate voltage. It's only by controlling the gate voltage that ID can change. So this is a feedback circuit in which things are arranged in such a way that Vg will go on changing if I naught is different from ID, and Vg will remain constant only if I naught equals ID, and the circuit will finally reach that steady state. Okay, so it's a feedback circuit. Now there are other variants of this. That is, we don't have to connect Vg to Vd directly. Okay, all we want is this kind of variation, Vd increasing, to be transferred to Vg in some way. There are many ways of doing it, so that we'll study. And also another thing to look at is, whenever we invent a circuit like this, whenever we come up with a bias circuit, we have to make sure that the transistor remains in saturation, because that's the desired operating point for an amplifier. Okay, so we have to check that as well. Actually in this case it must be pretty obvious to you, because VDS equals VGS. So this automatically means that VDS will be greater than VGS minus VT as long as VT is positive. So if we have a positive VT transistor, this connection ensures that the transistor remains in saturation region. Okay. So we will use this to make amplifiers. We will see variants of this in the following lectures.